learning and machine learning in general, which is model complexity and bias and variance. Okay, so I'm going to go over some basic terminology for statistical learning, and then I'm going to discuss this concept of a reducible and irreducible error, supervised and unsupervised learning, interpretability, and flexibility. So I think these three things, this, and this, are very important concepts. Okay, so I'm going to kind of skip through this, but basically statistical learning is the idea of using data and supervised and unsupervised learning to both predict and understand the data. So sometimes we don't necessarily want to, let's say, understand the data, and we don't care what the model is finding. We just care that the prediction accuracy is really good in data that we've never seen before. So that's usually how AI works these days. You see a paper and they, let's say they are very good at detecting objects in images, but we don't really care about how the machine is doing that. We just care that the accuracy is really high. On the other hand, you might care a lot about what the model is finding. What is the relationship, let's say, between the image and what the model is predicting to be, let's say, an animal or a fruit or something like that. So you might want to inspect the model. So there is this tension between prediction, accuracy, and interpretability. I think in science of science, we care a lot about interpretability, and in any social science, we want to understand what we're finding. So what is the relationship? Someone was mentioning, predicting success. What are the factors that are predictive of success? That's important for us. So statistical learning is a way for us to find those factors. It's a way for us to propose a statistical model and fit it to data and interpret those factors. And we can do it with, broadly speaking, with two types of learning. One is supervised learning, where we have data from the past and want to find relationships between the data and the features and some independent variable of interest. And the second set of methods called unsupervised learning, where we want to just understand the data. We don't necessarily have a signal that we want to predict, but rather than want to understand what is in the data. So some basic terminology, and this varies across fields, but in machine learning, usually you talk about features. These are the things that you want to use for making predictions. In some fields, such as statistics, these are called independent variables. I think in signal processing, these are called independent input variables, and so on and so forth. So in machine learning, you want to associate those features with some outputs. And again, that name has many different variants across fields. Some fields call it label. Statistics, they usually call it dependent variable. Now, in unsupervised learning, we don't have an output that we want to predict. The only thing that we have are the inputs or features. We don't really have something that we want to predict. So we'll focus first on supervised learning. So let's think about this. So let's think about this. I have three problems here that are about science of science. And let's take like a couple of, maybe a minute to think about what do you think the features are of these problems, and what do you think the outputs are? What are the things that we're trying to predict? Okay, so let's take a look at the first one. So this is a problem. Imagine that you have a research question, and this is what you're trying to do: predicted citations of a paper in 2 years based on author, journal, and affiliation rankings. Okay, so the question is, what are the features that you need for this problem, and what is the output of this problem? Okay. Okay, so I'm going to write here. Features and outputs of this. So any suggestion about what are the features that we need for that problem?
Features are the past values of citations.
Okay, the past use citations.
Yeah, I mean the values or the data we have.
Okay. Now, if you look at the very constrained description of the problem, we are not really using the past citations to make predictions.
One of the features can be the number of papers that the journal publishes every year, or every month, or every week, and the number of citations of the papers received in previous years for the journals, and number of publications of authors, for example, and yeah.
Okay.
Some of the features.
Okay, so I guess we have the citation, as someone mentioned before, and the features that you mentioned about the journal and the author. But in this particular example, I would say that the features are, yes, author information, journal information, as you mentioned, and affiliation rankings. Now, what would be the output that we're trying to predict, or the label of this problem?
Can I ask a question?
Yes.
Sorry. So the features are kind of the independent variables in regression. Yep. Okay.
Yes.
The outcome is output is the dependent, right?
Dependent variable, right?
Oh, okay.
So in this example, what would be the dependent variable or output or label? It's all the same. It refers to the same idea.
Yeah. Sorry. Go ahead.
Daniel, can I say something, please?
Yeah, please go ahead.
Okay, for the output, I can say that if the author is more exposed to the social media, so I think that he will get more citation as compared to the one who is not exposed to the social media, because I think his citation will get more attention if we take that, for example, in the context of altmetrics. So that particular article or that particular journal will get more attention as compared to the other one who are not exposed to the social media. What do you think?
Right. So I guess you're saying like social media activity, all metrics could be part of the independent variables used for predicting citations, right?
Yeah,
now, for this particular example, the output, the thing that we're trying to predict is, as Shadi is saying, the count of citations. But here we have to be careful, the count of citations in 2 years, right? So that's what we're trying to predict. So if you think about it, if we want to, let's say, find a relationship, we need data where we have information about all of these things, and then that will be like one set of columns in our pandas data frame, let's say, and then one column should be the citations that particular row will receive in 2 years. So this is like a count, okay? So that kind of limits the kinds of models that you can use. What about the second one? What will be the independent variables, features, input variables for that problem? I guess it's the same, right? So I'm putting the same thing based on these features. But what would be the prediction? What is the output of this problem?
Just a true or a false.
It's a true or false, right? So it's just a binary variable where they will break 50 citations, and it's a very specific. Like, I don't know if you've read this, but there are a good percentage of papers that are never cited, so they don't receive any citation. It varies a lot by field. So breaking 50 citations is actually a pretty high number for most papers in science. So it's a true or false. So can anybody, if you're familiar with the terms, can anybody say what kind of problem this is? One third of papers don't receive any citation. What kind of problem is this? Is this regression or classification? The first one, for example, is it regression or classification?
First one is regression, and the second one is classification problem.
Right. So the first one, we're trying to regress a continuous variable, the counts, but the second one, we're just trying to classify a paper into two categories, whether it breaks 50 citations or not. So it's binary, and it's usually called classification. What about the last paper? The last problem.
Excuse me, Daniel.
Yeah.
Here in the second problem, I have one question about the 50 citation. Let's suppose if there is a journal paper who got 50 citation in a low impact factor, but in contrast, there is a paper who is, let's suppose, cited in, for example, in Nature or in other another high impact factor journal, but they didn't reach to the 50 citation. So how we can compare this 50 citation?
Yeah, that's a good question, and at this point, we're not even worried about those more important questions. So once you start interpreting the models, like what this means to break 50 citations, you can start thinking about those questions, right? So there is this enterprise called citation normalization. So where you normalize the citation counts for the field, for the journal, even. So breaking 50 citations for maybe a physics paper is not as much of a big deal as 50 citations for a math paper, for example, just to give some examples. But that's it's part of what you're describing, is part of the interpretation of what you're finding. Okay, what about this last paper, this last problem? Can anybody say what kind of problem this is? What is the input, output? Is it regression, classification, supervised, unsupervised learning?
Sorry, it seems for me to just classification, because we are looking for the words and it's kind of selecting the most frequent ones like that. Yeah, could be. You can think of it as a classification. So you basically say, I have these inputs, which will be the abstract, and I'm predicting, I don't know how many key phrases are out there. I think the mesh library in PubMed, it's like 30,000 keywords. So you can say, I'm going to take the abstract and see which of the 30,000 keywords this abstract belongs to. Anything else? Any other idea?
It can also be unsupervised. Like we can use topic modeling, for example, and use like incoming abstracts, for example, and predict which topic the abstract belongs to. Right.
Very good. So we can look at the text, we can model this as topics, and then I guess take the topic of the abstract and use that to create key phrases. Yeah. So this is a field, and we'll discuss a little bit more about this you can think of this as natural language processing. We want to process the abstract, which is just natural language describing what the paper is about, and you want to do something with it, manipulate it, create key phrases and things like that. All right, so the idea of statistical learning is to take these problems and try to learn the underlying function that is generating this. So the underlying function that is taking the inputs and producing the outputs. So in the case of the first problem, such as predicting citations, we want to take the features, which will be the author citations, the author institution, the journal. Those are the features. I want to say we want to learn the function that is taking those features and producing the output, which was the number of citations produced in 2 years. Okay, so that's the whole idea behind statistical learning. So and of course, one of the main problems is, okay, what is that function? You usually don't know that function, and we make assumptions about what that function looks like. The other problem is that we don't observe the direct relationship between the input and the output. There is some noise associated with each of the observations, and we have to account for that as well. So in the case of the first problem, as I was saying, the X will be the author, journal, affiliation, rankings, and things like that, and Y will be the citations. So I have a data set here as an example. And again, as I said before, these notebooks are live. This is a presentation, and I loaded the data, and the data should be available. So if you execute this, it should generate what you're seeing. So you can play around with this at your own pace. So here I have an example of citation prediction. I have a data set of the citation of our article after 2 years, and I'm using the average ranking of authors, the average ranking of affiliations, and the ranking of the journals for making this prediction. So here I have the average author ranking and the citation count, and I created like a little histogram. I guess what's the proper name of this? Heat map? I don't know. But it's like a little, instead of doing the scatter plot, I have too many data points. I'm just showing, here there are little data points, most data points are here, and the color indicates the frequency of these locations. So I would say that we cannot tell much, but maybe there is a relationship with the average author ranking and the citation count. Now, so the higher the ranking, yeah, unclear. But so that's why we need to use some statistical model. So here's the affiliation, the ranking of the affiliation. It's hard to tell what's happening, but this is just the data. And what's the next one? The ranking of the journal, I don't have it here. This is just 2 examples. So what we can do, we can say, okay, we're going to assume that the data is being generated, and I'm going to kind of skip this a little bit, move fast, but basically we're going to assume that the data that we're seeing, the rankings and the citations are coming from a distribution. That's the basic assumption of statistical learning. But we don't know the distribution, so we want to learn it. And the idea is that you want to say, okay, I'm not really observing the direct, view of the function that I'm trying to learn, but some sort of modification of that function based on some noise. Okay, and that noise could be all kinds of stuff. So that noise could be from the system, or it could be outside the system. It's just some variability that happens in the data and in the process. Okay, so so this is saying if we look at this in 2 dimensions, so if, let's say we have just one feature and we're making a prediction of another feature of one output, you can say, okay, for any given feature value, there are multiple outcomes because there is noise. Okay, so we are assuming that it should be one, but because there is noise, there is this variability around the area that we're trying to predict. Okay, so first we want to do two things. So let's see, we want to do two things. We want to first estimate f, and we want to estimate this function because we want to make predictions, or and either or. We want to do inferences. We want to understand what's happening. Okay, so how do we estimate f? In statistical learning, we make an assumption about the model. And we say, okay, we're going to make an assumption about this function. So we're going to say we're going to estimate, let's say, the outcome based on an estimated relationship between the features that we're measuring. And but we know that we will be making mistakes because there is some error. Okay, so the next slide will explain a very important concept in statistical learning that is kind of obvious if you think about it, but it takes, the next slide kind of takes the mathematical way of explaining it. So let's say we have through the data that we observe. Okay, so y without a hat is the data that we actually observe. But imagine these are the citations for a given paper in 2 years based on all the features that we were discussing. And imagine that y hat is our prediction of that. Okay, so imagine that we learn that, let's say, it's important to have good ranking of authors and journals, and we're making a model that makes the prediction of citations. So we can measure the error that we're making in our prediction by computing the square difference between our prediction and the actual value. Okay, this is typically called square error. It's a very standard way of measuring how much what is the size of your mistake without regard to the side of your mistake. It doesn't matter if it's positive or negative. Now, I won't go into details, but basically you can decompose this. You can just replace the equations that I was showing in the previous slide. And you can show that this difference boils down into two components. One component is how much your function that you propose, your assumption about the underlying f, how close that function is to the real function. And this is called reducible variance. So you can get very clever and try to guess what the real underlying function is producing the data. And as you can get very, very clever about that, and you will reduce the error because you will reduce this variance. But there is one part of the error that you cannot reduce, and that part is called the irreducible variance, and that has to do with the noise in the system. Okay, so sometimes you have to be careful when you're modeling data to realize, okay, are you trying to reduce errors that are reducible, or you're just, wasting your time? You want to make sure that you don't waste your time trying to reduce errors that are impossible to reduce. Now, why do we estimate f? Imagine that we have estimated f, we found a solution. So, well, we want to do it for multiple purposes. One of them is just to understand. So, for example, which predictors are associated with the outcome? So, do we need to have journal ranking for predicting citations? Maybe we don't need the journal ranking. Maybe everything's related to the author. Relationship between what we're trying to predict and the features. Are citations higher for higher ranking affiliations? And you can have questions about whether you are using the right features to predict the citations, for example. So someone was mentioning maybe you need social media to do this, so maybe you will need to augment the features that you're capturing. Okay, so now the way that you estimate f, you have different, like two big families of methods. Usually we use parametric models in statistical learnings, and I won't get too much into non-parametric models, but you can use something like nearest neighbors to make the predictions. But usually you want to do something like a linear model to understand what's happening and understand the relationship between the features and the outcomes. So I'm going to skip this and you can go over it yourself. But this is just saying, okay, let's say we assume that there is a distribution producing the citations, and the distribution is based on a Gaussian distribution. Now, the Gaussian distribution is not the greatest assumption for citations, because citations, as you see, are not normally distributed. But the more interesting case is that, let's say you're trying to predict the citations based on the author ranking. And you can say, I'm going to assume a linear relationship between the author ranking and the citations. And to do that, I will learn parameters based on data. I will learn the intercept of my prediction and the slope. How does the author ranking influences the citations, and then plus some noise that I don't know. Okay, so this is the data. I guess here it's a little bit better. So I guess it's unclear what's happening, but because it's just too dense. So let's the machine do the work for us. So if I run this, I can say, well, I want to minimize the difference between my prediction, my model, and the actual observation. So I can assume a square error difference. I can optimize that. And there are many, many ways of doing that. With regression, you can find this solution by applying this equation. This is called you solve the solution. You solve the regression immediately by doing this operation, but you don't need to worry about that too much, because you can do it with Python. So let's skip this part. And this is what I found. So I ran the model, this prediction citation based on author ranking. And I found that the citations are 106 minus this. Okay, so it's a little strange, but it's saying that to predict the citation of a paper based on the author ranking, you could use this equation. Okay. So this is usually what you will get out of a regression analysis. Okay, so so question for you. So how can you interpret this? What does this mean? If your method finds this equation, what can you extract out of this to try to interpret the data?
You want author ranking to be small?
Yes. So the smaller, well, yes, the smaller the author ranking, right? The smaller this number, you will reduce this negative, and you make the citations bigger. Now, why would the author ranking be small? But I mean, and if I guess you need to know Microsoft Academic Graph. But the Microsoft Academic Graph uses and I think OpenAlex does the same, a ranking. So ranking 1 is the highest ranking in the data set, and it's based on some on something called the PageRank algorithm. So they use that. So this is basically saying the higher the ranking of someone, in high in the sense that the smaller the number, the better. Okay, someone who is like very famous will have a ranking of 100. Someone who is just starting in a field will have a very, very large ranking. And this is how it looks like. Now with the data, it's really hard to see, but you see that maybe the density of here is not that high, but this is what's happening. Okay, so regression versus classification. In regression, you're trying to predict a continuous number. In classification, you're trying to predict a set of outcomes, and there is usually not a relationship between the outcomes. I'm going to skip this. So I'm going to transform the previous problem into a classification problem by trying to answering this question, whether a paper will break 50 citations. Okay. So here I'm plotting it with this a kind of a way of like I kind of jitter the data. So I have in 0 is like these are not highly cited papers, but I kind of spread it around so you can see the data more clearly. And these are very high. These are highly cited papers. These are papers that break 50 citations. And as you can see, most papers, at least in the data set that I have, don't break 50 citations. So how does the author ranking affect that? And you probably can see that on average, most of the non-highly cited papers have a higher author ranking than the highly cited ones. And to do that question, to answer that question, you can use something called, for example, logistic regression that does the learning for you. And okay, so another very important concept in this is the idea that some models are very easy to interpret, but are not very good at the accuracy that they have. Okay. So usually simple models are not very accurate, but are more interpretable. So this plot is from the book, from one of the books that I'm using. I think it's called Introduction to Statistical Learning. You can see this set of models to be around here. So this squares is regression. Lasso is like a regression, but when you have selection of variables. They're not very accurate, but they allow you to interpret the data very, very well. And you can make, suggestions about what the underlying signals are. Complex models are generally more accurate, but less interpretable. So once you get into these kinds of methods, Bayesian boosting, like if you know random forests or gradient boosting or deep learning, for example, they're very accurate, but they're not very good at telling you what the model is finding. So if you're trying to find the relationship between, author rankings and all kinds of features about the journal and citations, you will get very accurate results with random forest, but you won't know necessarily how that relationship is happening. Okay, so let's do a little activity, and let's serve as some sort of a break. So let's see, 11. So it's going to be 11. Okay, so let's I'm going to create breakout rooms so that you can discuss these two questions, and I will do it at random. Okay, because I'm going to break out the breakout rooms that I created before. So this is 7. So let's see here. Okay, so that you can discuss this. Okay, so the first question is, think of a supervised and unsupervised problem of unsupervised and unsupervised problems in science of science, and think of 3 problems either requiring these combinations of features: prediction but no inference, inference but not prediction, and prediction and inference. Okay, so let's take like 10 minutes to discuss this and see what happens. I'm going to share this with the breakout rooms. All right, welcome everybody. This is the last session of today. So today we don't have talks in the afternoon. We just have the group sessions, but those are on your own to discuss the project. And of course, you can do it on your own more comfortable time if you are all part of the same time zone. So now I'm going to review a very important concept in machine learning, which is this idea of generalization of performance, and which leads into underfitting, overfitting. And I'm gonna use scikit-learn to explain those concepts, and it will be also an introduction to scikit-learn, which is the package that runs many different machine learning techniques. So by a show of hands, how many of you know scikit-learn? You can like thumbs up. We've heard, okay, 3. Okay, so not many of you, which is great. Scikit-learn. Okay. It's okay. Everything's good. So that's perfect, because then it means that this will be a very productive session. Okay, so before in the previous session, I kind of tried to explain that we try to fit a model to the data, but that's one part of the problem, is try to learn from the data in a supervised fashion. But what you really want to do is to try to generalize what you're learning to new data sets, and that's part of the model evaluation and generalization performance. And we're going to take a look at that for regression and classification. So, and it has many slides, so I'm gonna like skip a couple of them. But basically, what we want to do, we want to learn a model so that it has very good performance on data that we have not seen before. That's what generalization means. We want to basically take a piece of data that we will call training data. We will say fit our linear regression, random forest, whatever we're using, deep learning, fit it to the data as much as possible. But then we want to make sure that whatever it's learning, it will also perform well in data that we didn't use during training. And we call that data test data. Okay. Now, the way to do that, and you can take a look at that by you can kind of formalize that by saying, okay, we want to learn an estimator, let's say f hat, and we want to measure its performance in data that we've not seen before. So that will be y, capital Y here. And you can have different generalization performance metrics. For regression is usually the square error. For classification, it could be something like accuracy, or there are other ways of measuring. So mathematically, we want to measure this. Okay, we want to say, okay, for a given training set, we want to measure the error that we're making in data that for the entire data set. Basically, this is like the dream where we have like infinite amount of data. For a given training data set of a certain size, we want to see how well the loss function will be for the entire distribution of data. Typically, this is not possible to do. So what we end up doing is something like cross-validation, where we're reusing the same data multiple times. But that's okay. All is good. Okay, so examples of errors, as I was mentioning before, you have square error, root-mean square error, which is just the square root of the previous quantity, and the coefficient of determination, the R square that I was mentioning before. Okay, so the proper way of doing this is, it can be confusing sometimes, and many people get this wrong. And by many people, I mean people who are, professionally doing this in their day-to-day job as data scientists or machine learning. Okay, so imagine that you have a phenomenon that you want to measure, that you want to model, so let's say citation prediction. I apologize if you hate citation prediction, but that's just our working example here. So you have a data set on citations, and you have many features that you will use to make predictions about that. Now, the idea is that you want to suggest multiple possible models that will explain the data. So it could be different kinds of models, let's say a linear regression, random forest, deep learning, okay, different kinds completely. Or it could be models that are kind of the same kind, but with more variables or less variables. So for example, okay, you're going to try linear regression, but you're going to try a very simple model, let's say with one variable. Does the H index of an author predicts the citations of a paper? How good is that prediction? Or you can go crazy and add all kinds of features, the social media presence, the institution ranking, and things like that. So you can have a very small linear regression and a very large linear regression. Okay, so the idea is that you have this candidate set of models that you want to try. And the outcome of this process that I will explain will be, okay, this is the best model that can explain the data that you have. Okay, and the proper way of doing it is as follows. You will take your training data that you have, and you will split it into 3 pieces. Okay, and the kind of the breakdown of this differs, but you can think of, okay, training will be like maybe 60% of the data, validation will be maybe 30%, and testing could be 10% of the data, something like that. Okay, and what you will do, you will try all your models to fit the training data. All the things that you listed, you will try it on them. Okay, so you fit the models in the training data, and then you evaluate how well those models do in the validation data. You fix the model, so they learn already in training, and you see how well they do in validation data. And then you, based on that validation data, you pick the best model. And that's what you use for measuring the performance of your process. And you use the testing data to do that. Okay. And I will kind of I will re-explain this because I think it's such an important concept. And I kind of found this cute app that allows me to draw, and I have my device here that can help us. All right, so let's assume that you have a candidate. Let's say you have a data set, training data. I'll call it just, maybe I shouldn't even call it training data. I should just call it data. Okay, so you have your data. Okay, this is the data. And what you will do, you will separate it to 3 steps: training, validating or validation, pardon my handwriting, and testing. All right, so you will say, okay, I'm going to try all these models, okay, and I will call them M1, M2, blah blah blah. You will try, n different models, and this could be, linear regression with more variables, random forest, whatever you like. Okay, so you will fit these models to the training data. Okay, you will learn them based on this data. Okay, so what I will do, I will say, okay, once you fit this model, then you will have and let's say an M hat, I will say M1 hat, which is your estimation of that model based on the training data. Okay, so as the example in the previous set of slides was, okay, what is the relationship between the author ranking and the citation? You learn the intercepts and you learn the slope, and that was based on the training data. Okay, then you measure the performance on the validation data. Okay, you don't fit anything, you measure performance, and I call this perf. Okay, you measure the performance. And you measure the performance, and then you will get, let's say, the law, I will call it L, okay, L1, say the loss, like how much error you're making, let's say, of each of these models. And then you pick the loss that is smallest, okay, the best model. Okay, so imagine that the best model is this one, okay, and I will call this the asterisk, okay. So imagine that's the best model for the validation data, and we're going to call that I'll call it asterisk, which is the best model, and maybe I should put the asterisk as a lower part here. So imagine this model 2 is the best one in validation. Okay, so then you measure the performance of this model on the testing data, and that becomes your generalization error. Generalization error. Okay. So this is the basics of how you evaluate different models. Okay, this is how you should do it. And many people don't follow the rules, but you're lucky that you're taking in this summer school. So typically, people, well, not typically, I guess this is something that I use. Typically, this is like 60% of the data. This could be like 30%. This could be like 10%. Okay. That's how it works. Any questions?
Yes.
Excuse me. May I ask you, people usually skip validation set, yeah?
Yeah.
What are okay.
Yeah, people usually report this performance, these little L's, and they pick the square, the asterisk. And that's the main mistake that they make. The problem is that this asterisk is overfitted to the validation data. You want to see, okay, once you select the best model, you want to see how well it does in the testing data.
How do you divide them up? 60, 30, 10? Is it just a random sample, or you can't?
Yeah.
Right. You can't
Oh,
go
yeah.
by, keep the most recent years for the test, because that might be different. How do you ensure that the data is representative on all these 3 steps?
Yeah, that's a great question. So depending on the nature of the data, you want to do this more carefully. So if the data is temporal, I know that some of you are interested in temporal trends. Then you want to do kind of what you're saying. You will say, okay, you have time, and you have your data. So you want to say, okay, I'm going to use time as a way of splitting my data. So you might want to say, okay, I'm going to use this as training. I'm going to validate here. And then I'm going to test this here. So you should use time as a signal for you to, or as an index for you to validate properly with temporal data. The same thing happens, let's say, sometimes you have data that is like multidimensional. So let's say you have authors, and then institutions. So you have authors that belong to different institutions, but let's say you want to find something about institutions, which institutions will, grow in their ranking in the future, for example. So you want to validate your model based on institutions. So what you want to do is you will pick authors, but you don't want to pick authors from the same institution and put them in the same buckets. So you want to say, okay, this is going to be my training data, validation, testing. So you want to use the authors that are here as your training, but you don't want to use authors that are in the same institution in your validation. Okay, so let's say if I'm testing a ranking for University of Colorado, I don't want to take, me in the training and then in the validation Aaron closet, because we belong to the same institution, so we're kind of cheating in our prediction.
For the time example, though, what if the performance is different from training versus test? Like I'm looking at number of open access articles over time, right? You draw an exponential over that.
Right.
The training area would probably behave differently than the testing area. So maybe the model isn't valid anymore. How would you get around that?
Yeah. Yeah. So you want to, if you're assuming that there is hopefully you want to have a model that will capture that in the sense that, let's say, there might be still some exponential growth here in the training. So you want to capture some of that exponential growth, but something that is independent of time. So maybe the rate of that growth. So maybe the rate of that growth is the same, right? So it's the same exponent. So hopefully your model has that variable, that unknown in the model, so that you can learn it from training data. But it's yeah, there is this problem called generalization and basically data shifting, in that, you know, that in the future, unclear if the same will hold, and that's just the nature of the problem. I mean, the main thing that you want is you want to reproduce in your data what will happen in the future. So if in the future what you want to use is to use your model for making prediction, you know, 5 years from now, well, you should try to reproduce that process in the training data that you have, in the data that you have. So do it in the same way. And there is no, like, you know, there is no perfect solution, and everything varies depending on the situation. That's the world we live in. Okay, but now there are more complicated exams. Any other question before I kind of continue digging deeper into this? Okay, so there are sometimes even more complicated examples where you have models. Let's say you can have a let's say if you're familiar with random forest, for example, you might have a model M1, and but then the random forest might have like another parameter that is like how many trees you're going to use. So it's like M1, but it's like you add a dimension to M1, so you can have like let's say random, you know, M1 could be random forest, and then M1K could be random forest with K trees. So you have these kind of nested models that are more complicated. So you want to be careful with that, that you kind of train them on the same data too, without thinking that the K kind of you want to kind of overfit the validation, say the data with the K, with the number of trees. So this is the basics of validation, and you should all try to follow this. This is the proper way of doing it. More importantly, if you see papers that publish without doing this properly and comparing models properly, you should complain. you should say, you know, this is overfitting. So this is like another version of p-hacking, and you're probably familiar with this. You're probably familiar with the reproducibility crisis, although some people don't like that term, but basically, you know, studies, you can think of these M's as like group of scientists too, like they're trying to study specific set of data, but then they overfit the data, and therefore they're claiming something about a specific phenomenon that is not generalizable, because they're basically overfitting, because they p-hack their way into finding into running their study. All right, so that's how you should do it. And once you do this, you will get this number in the end, and that's what you will report. Okay, but to do this step, you can do it in scikit-learn and in Python, and they have functionality that does it for you relatively easy. Now, one of the problems with doing it like this is that you lose a lot of data. So if you're using 60% for training, you're losing 40% of your data because you're not fitting that data. So the way to solve that is a method called cross-validation. And I won't go into details, but basically you shift around, you train on one set, and then you validate it on a different set, and then you kind of shift around and you use the validation from the previous iteration as training, and you repeat that many times. Okay, so there is something that happens when you have, let's say, I was mentioning before this idea of random forest, or let's say linear regression, where you can have a regression with one, let's say a very few number of parameters, or a regression with a ton of parameters. Okay, so when you're measuring generalization performance, there is this phenomenon called bias and variance trade-off. And the idea is that if you kind of mathematically examine the error that your model is making, you now have a decomposition of the reducible error, the thing that we saw in the last set of slides, into two components. One is bias square and the other is variance. Now, it's the intuition behind this is to say, if you have a high variance model, means that your estimation has high error bars. You're making, you know, maybe you're accurate, but you're on average you're accurate, but each individual fit of your model will be very, very different. If you have high bias, you might be inaccurate, but at least your model will be the same with each data fit. Okay, and the idea is, so I have a little example here. I hope this works. So I have this. Imagine this is the data that we have. Okay, these dots are the data, and the underlying function is this exponential decaying, like a power law thing. Okay, so this is the function that is producing the data, but we're adding noise around it. So I could sample from that data. So imagine that I get different data points. Sorry, I have different samples of data. So imagine these are like different observations from different parts of the world or different journals. Like each of these represents different sets of data, and you see that there is some variation because of the noise. Now, if I use a very simple model to model this data, like a regression model, you will see that it will find a line relating the X and Y. And every time you fit it, it will be very similar because it won't vary a lot because it's very simple. Okay, it will require very little data to find the parameters. Okay. However, if I use a more complicated model, such as nearest neighbor, so I just look at the nearest neighbor data points, then the fit becomes really jittery, and each data set will be different, will produce a different fit. Okay, so now if I use more neighbors, so let's say if I use 20 neighbors instead of one, the fit will be smoother because I'm using more neighbors to find the prediction. Okay, so if I put the two models, the nearest neighbor with very small number of neighbors and with a lot of neighbors, you can see that there are differences. Here is very jittery, but it's very close to the function, and here is very smooth, so it doesn't vary a lot, but it's far away from the function. And I'm going to kind of zoom in. Hopefully that works. So you see that the red line here is very far from the blue line, whereas here the red line is always very close, but it varies a lot. Okay, so we will say that this has high variance because each of the models is different, but low bias because it's very close to the blue line, whereas this model has low bias because all of them, sorry, low variance because each of the fits is basically similar, but high bias because the fit is far away from the blue line. Now, you don't need to worry about any of this nonsense if you follow the proper trademark way of doing the fitting. Okay, so if you follow this, it shouldn't be really a problem. If you do it properly, you will find the best model, the ones that has the proper balance between bias and variance. Okay, so I think, how much time do I have left? Okay, carry the one. Do I have like 35 minutes? Or no, 10? Yeah, I think so. Okay. So that's the basic of it. And okay, so I will show you a demo of this with real data. Okay, why not? So I'm going to load, and someone I think mentioned ggplot. I forget, I talked to so many people, but there is a version for that person who mentioned ggplot. There is a version of ggplot for Python. So that will make that person very happy. And it's called Plot9. Okay, so I have a data set of this example where I'm trying to predict the citations of someone. The citations of a paper, sorry. based on the journal rank, the average affiliation rank, and the average author rank. Okay, so I have that data. So I'm trying to, this will be my features and this will be my outcome. And I'm going to use ggplot to produce the plot of the different features. Okay, so I'm going to skip this. Okay, so I'm going to first run a very simple model. I'm going to say, and this is the name of the package scikit-learn is sklearn. So I think the historical name is scikit-learn because it was like a scientific kit, and they used to have different types of parts of this kit. So one was learning, the other one's images, etc. So, but now some people call it sklearn. Okay, so from scikit-learn, I will use a linear model. Okay, so this is just linear regression. My features is just going to be the average author ranking, and my prediction is going to be the citation count. So I will fit the data, and I can, so this will be a linear regression. So basically I will have, I think I have it before. I have, let's see, citation equal some intercept plus that, and then I think I had author ranking, something like that. Would that work? Perfect. Okay, so that's what I'm trying to do. I'm trying to model citation as some intercept plus some coefficient times the author rank. Okay, so the intercept that I found is 106, and the author rank influence is minus 0.005, and you can show it in ggplot. I think automatically finds a line. Okay. So, but now let's do this properly. Okay, I've been talking about how to do this properly, and this is how I will do it. Let's see. Okay, let's forget this. Okay, here. So I will have my list of models. Okay, so I'm going to go back to the whiteboard. So I have the list of models that I want to try. Okay. I have the list of models. I'm going to try 3 models. Linear regression, random forest. I would try 10 trees. And if you don't know what this is, don't worry too much. It's just a very complicated model that you use decision trees. So it's shown very good performance, but it's hard to interpret. And the third model that I will try is something that has 500 trees. So this should be simpler than this one. And this should be the simplest. So I'm going from simplest to more complex. So I define the models. Now what happened? I think I have to import all of this first. Okay, I'm going to define this. And now I'm going to do the split. Okay, I'm going to do train test split. Okay, and here what I'm doing, so I have my X and Y. So if I do X are my features and Y are the thing that I'm predicting. So I have 79,000 articles, and I'm gonna take the first 1,000 and I'm going to split that into training and testing. So I'm only going to use 1,000 data points. And I think the reason I did that is because I think it took too long to fit or something like that. So I will train it on the training set. So this function splits the data into training and testing. So I will train it on the training set. And the last model takes, a little bit more because it's 500 estimators. So let's see, what is this measuring? Score. I think score computes the R square. Okay, so this is the coefficient of determination. So it's a pretty good R square, 0.82%. So this is the training, but of course the training is like not really useful because we might be overfitting the training. So the real test is to actually try and we'll cross-validate the model. Okay, so we are going to validate it with this. We're going to pick we're going to do cross-validation on the training data. So this will automatically give us the mean validation. So it's a little bit more sophisticated. And as you can see, the regression is the best one. So on validation, it actually has 10% R-square, but the other ones have negative R-square, negative coefficient of determination. So that's pretty bad. So this basically is other models are overfitting. Okay. So I do this step. I go here. I have these L's. So these are the thing that I computed. So I'm going to pick the best model based on those L's, and that's going to be this one. So the best model for me is model 1, and I will now fit the training data because I will use all the data, and I will see how well I do in the future with testing data. Okay, so the testing data is very close to the validation data, and you saw that there was some variation, and that's because this is doing it at random. Okay, so I should report this as the performance of my model. I shouldn't report this. Okay, if you're reporting training performance, you're doing it wrong. You should report the testing performance. Okay. Okay, so I have that. And these are the coefficients, but the model 1, I really use only one feature. So it's the same that was before. Okay, so any questions about this? So if you're gonna use any, if the person who is doing like success prediction, I think a template like this will be very useful for that project to compare different models. But any other project that does some prediction and interpretation could use something like this.
Yeah, may I ask one question?
13 line, I think. X test, X train, but we don't split cross validation set.
Yeah, very good question. So here I kind of cheated a little bit in that I'm using this function, cross-val score, and that does the validation in the training. So I'm doing the following. Oh, sorry, go ahead.
It takes a little bit of items from training set and don't.
Yeah.
Okay.
Yeah, exactly. So it does that. So I do have the train, the test, but then I do cross validation on the train. So I do like train val, and then I kind of shift the val around. So this will be val, train, then validation and training. So that's what it does. So it does the validation inside, and it kind of it's easier to apply. Any other question?
Okay, I have one question. To do this, should we consider the endogeneity problem in the model? Should we consider that, or if how to found this problem and to solve it?
So should we? Can you repeat? I didn't catch that. Should we consider what?
Endogeneity problem.
Oh, the negative.
And the endogeneity problem between the model, the relationship between the features something like that.
I kind of not. You mean this? The coefficient?
I write it in text in the snack.
Oh, heterogeneity. Oh, yes. Well, here we're kind of, as we're not making, I guess one of the problems with machine learning is that people don't care too much about these issues. So statisticians are very careful about this, like endogeneity. What is the other word that is very long? Heteroscedasticity or something like that. You want to make sure that the data is conforming to the model that you're assuming. So let's say if we are assuming a linear model, like the first one, you want to make sure that the data is actually a linear relationship. And here, I don't think it's a linear relationship. So the model is kind of making wrong assumptions. Now that becomes important when you're trying to do statistical tests, and some tests need to have those assumptions. So let's say you're doing like a t-test or something like that, or ANOVA chi-square test. If you don't have the right, if the data doesn't conform to the assumptions, then the test won't work. It will give you a number, but these results won't make sense. Here, we don't really care, to be frank. I don't think in machine learning people care too much about those things. So good that you're worrying about those things. Good for you, but unless you're doing statistical tests, you should just worry about the performance that you're getting. Yeah, I will just go, well, it depends. Like some models are easy to interpret. So if you want to really understand the data, so let's say if you're in science of science, usually that's what you want to do. You want to try models that are very interpretable, very easy to understand. So maybe you want to try models that are simple to understand, and but you shouldn't worry too much about the performance. So now, if you don't care too much about interpretability or inference, you should just try as many models as you can with the computational power you have. So I don't know if you've been following, or if you, like the entire audience, have been following the developments of AI recently. But some of the models, like someone mentioned EDAL or something like that, and they take millions of dollars to train. You need literally hundreds of GPUs to train those models. So if you have the budget to test those, good for you. But sometimes in academia we don't have those budgets, and we have to conform with simple models.
May I briefly question? Why we use R square here? Is
no
we can
reason.
use everything else.
Yeah, we can use whatever we want. I think, but that's a good question. So model 1, any of these models have a function called score, and I think it uses R square by default, but I think you can. Oh, it doesn't. Okay, so I know maybe there are other ways of measuring the performance, but I'm not familiar with them. But we could use square error, whatever you like. Okay, so there is another notebook about scikit-learn that I borrow it from a book, from the book by Jake, and it goes through more than just than supervised learning. It goes through unsupervised learning as well, but the data set are not related to science of science.